Welcome and hello. This is a video exercise in HEC HMS. And in this exercise, we are going to be creating an interpolated precipitation grid over Michigan. That was just the specific idea I had in mind. It could be any type of grid that uses the interpolation method, and it can be any location. It doesn't have to be Michigan. All right, but what you're going to learn from this exercise is the basics on how to create a grid using an interpolated process using time series data sets from known locations. All right, so let's go ahead and get started. Right now, I just have a blank HMS. There's no instructions or web pages or initial files to download. This is just me kind of freestyling it here. So let's go ahead and start by creating a project in HMS. Go up to File, New, give that project a name, and then click on the folder icon to navigate to the location you want to save that project. Okay, I'm going to put my project here, US customary units, and then create. We now have our project created. Let's start by creating a basin. New. I'm just going to call my basin basin 1. And then next what we want to do is assign that basin a terrain data. We don't have terrain data right now, so that's what we're going to do next. When we use these interpolation types of processes in HMS, our subbasins and gauge locations need to be geo-referenced. So what we're going to do is head over to the USGS website right here, and then find a good location in Michigan. I'm going to choose this River Rabbit watershed right here. It's in Western Michigan. And let me just go ahead and on the left panel, click on the elevation products. I've had good luck with one arc second, so let's go with that. I will leave a link in the description to this nationalmap.gov/downloader page. It's a USGS website. So what I'm going to do is aim for this location right here. I'm going to scroll up and then click Search Products. It'll search the area that I'm currently located in. So if I hover over the maps in this left panel, it'll show me where on the map that TIFF data that I download is what area it covers. So what I'm going to do is just select this location as my outlet, even though the river does extend a little bit further into, what is this, Lake Michigan. Okay, Lake Michigan. Sorry, not from this part of the country. I'll go ahead and download that TIFF. Wait for that to download. All right, so that's completed. I'm going to go ahead and move this TIFF file into the terrain directory. So here's my project. Here is the terrain directory, and I'll just do that. All right, that's moved over. Next, let's go ahead and import that data into HMS. So I'll go to Components, Terrain Data Manager, New. I'll just call it Terrain 1. That's fine. It's our only terrain data we're going to be using. Then click on this folder icon and navigate to that TIFF file, which is in our terrain directory right here. Okay, click Finish, and then we can close that. Here is the terrain layer right here. So now in our basin, with the basin selected in the Watershed Explorer, let's go down to Terrain Data. And I think I have to save. Let's see, okay, let me just click Terrain Data, click Basin. Now is it an option for me? There it is, Terrain 1. So I'll make that selection and then click Save. It's asking me about a coordinate system, and yes, I want to select a coordinate system. This is going to be UTM zone 16 north. So let's go to UTM, and then this is going to be 16. It is latitude band P, in case you're interested. Set, and that should pop into place. There it is. All right, looks good. If I go back to my map overlay, the Rabbit River leaves this map through the west edge, and there's also another river right down here. I'm just getting my general bearings here, about a third down from the north edge of this map panel. So let me just take a quick peek here. So we have the Rabbit River, and then this is the Kalamazoo River. See if I zoom out a little bit. Yeah, so this is Rabbit River here. This would be the Kalamazoo River. So I just need to make sure that I zoom in on my location. So I know that the outlet point I'm going to place is right around here and not further down here for Kalamazoo. All right, let's get started on these GIS tools. We're going to skip terrain reconditioning. That's not needed except for specific situations. So we'll go with pre-processing sinks and just work our way down that GIS menu list. All right, that completed. Next up in the GIS tools is pre-processing drainage. Okay, the pre-processing drainage step completed. It took about 2 minutes for me. I edit the videos so the viewer doesn't have to wait, but just so you know, that pre-processing drainage step usually takes the longest. All right, so let's go ahead and toggle off some of these layers because I don't need to see them all. So map layers, the four that I just created. In fact, I don't need to see any of those. Next up is going to be the identify streams layer. So this is sort of a trial and error here. I'm going to go with 30 miles and just see what happens. All right, so that's done. It looks like our stream is right here. I'm going to change the draw properties real quick just to make it a little bit easier to see. I'm going to change it to classify and then manual. And then down here, I'll say there's two different classes. Extend this down a little bit. All right, so the non-water is going to be white, okay? Or I should say not enough water. And then the water for the main stream will be blue. I'll put a threshold at 10 here and then something large like 10,000 and apply. Okay, cool. So now we can clearly see this is the Rabbit River outlet. And then just to confirm, we should have another outlet down here. Yep, so that's for that Kalamazoo River. Great. So we can go ahead and zoom in now and put our outlet point at, near the base. That looks good. And next is to delineate elements. So I'm going to type in subbasin, reach, yes, junction, yes, and delineate. Okay. All right, looks good. It zoomed me out to show all the subbasins. It looks like there's about 5 subbasins. I could change that area to larger than 30 square miles, but it's not too much effort to merge these subbasins. So I'm just going to hold down Control, single left click on each of these subbasins, and then merge them. Here's the last one. So with those selected, I can go up to GIS, merge elements, and boom, looks good. Now I'm down to one single subbasin, which is 275 square miles. So fairly large, but as you'll see from this exercise, we're not actually going to be looking at the hydrologics and measuring outflow or trying to calibrate anything. This is purely a matter of getting a subbasin on the map that is geo-referenced so that we can use the interpolation tools that are built into HMS. It is worth noting that we do have a latitude longitude here. If we go up to GIS, we do have a coordinate system in place, and then we'll also need to put the lat long for our different precipitation gauges. While I'm working with the subbasin, I can go ahead and make some edits. I'm going to turn off some of these layers first. Okay, looks good. So what I'm going to do for discretization is I'm going to say this is a structured discretization. Go to the discretization tab, and then I want to use UTM 16 north. And then the cell size is going to be smaller than 2000. Let's go with 500 and then click save. Let's go ahead and generate those grid cells. So GIS compute grid cells. Okay, so that got calculated. Let's toggle on that layer so we can just confirm that it's appropriate size. Okay, that looks good. It's sufficiently small. It could be a little smaller or larger, but as you'll see, that's good for this exercise. I'm going to actually turn them off now. Okay. Let's see, back to the subbasin tab in the components editor. For the loss method, I'm going to say none. For the base flow method, I'm going to say none, keeping this real simple. And then for the transform method, I'm going to use mod Clark. I believe the user's manual says I need to use either mod Clark or 2D diffusion wave right here down here at the bottom. But we're going to go with mod Clark. And then to specify some parameters, I'll just be very generic and say 10 hours and 10 hours for the time of concentration and storage coefficient. We're now ready to place some precipitation gauges on the map itself. And I chose to create a hexagonal shape, a equilateral hexagon that's more or less centered in the middle of this subbasin. Not because it's realistic, just because I thought it would be cool, just to demonstrate that the exact location of the gauges within your subbasin or outside the subbasin could be random. Same with the time series data associated with that gauge. And again, this doesn't have to only be for precipitation. That just happens to be the parameter I'm using. All right, so to do that, we'll go up to Components and then Time Series Data Manager. Precipitation gauges is the one we want, but just so you know, there are a lot of other options. So I'll click New. Gauge 1 is fine. I'll click Create. And at this point, I would typically create gauges 2, 3, 4, 5, and 6. But as you'll see, it's a little bit more easier, more efficient to create one add some data, and then make a copy so I'm not having to do repetitive work. All right, over here in the Watershed Explorer, we have our precipitation gauge number 1. And what we're going to do is select DSS record. So what I need to do now is leave HMS, create that data in the DSS file and the path so I can come back to HMS, assign it, and then repeat that for the other 5 precipitation gauges, which have not even been created yet. All right, so what I'm going to do is head over to Excel. And what I've set up here is a spreadsheet that's going to be for an hourly time step starting on January 1st, 2020. So that's what these first 5 columns are right here. And then I'm going to have data for incremental precipitation gauges 1, 2, 3, 4, and 5. What I did was I created a equation based on a sine function and just scaled it down to a reasonable precipitation. So these precipitation values for gauges 1 through 6 are ranging from 0 inches per hour up to 0.2 inches per hour. Yeah, so right here, 0.2 inches per hour. And they are all out of phase by 1/6 of the total period. That way, the precipitation distribution is equally spaced. If I go ahead and plot these 6 gauge data for the first period, which is the first 5 days, then you can see what that looks like. So they're all going to be out of phase with each other by approximately, I did a 5-day period, so that would be 5/6 of a day. Is that 20 hours? Okay, anyway, so 120 hours right here. You can see that it starts at one spot, goes down, and then back up to whatever color you're looking at. All right. So anyway, that is what I did and built in Excel. There's no reason you couldn't build something like this. Choose your own shape, choose your own pattern. The sky's the limits. Next, what I want to do is go into DSS view. And first I need to create a DSS file to serve as a container for the database of these time series data sets. So let's go ahead and do that. I'm going to go File, New, and then I'm going to put this in my data directory. All right, so here is the project. I'm going to go Data, and this is just going to be called data.dss. That's fine. It's being created. We have this little tab right here representing the file itself. There's no paths in this DSS file yet. That's fine. I'm going to go ahead and go to data entry, manual time series. Part C, I'm going to use precip-inc. And then for part F, I'm going to call this gauge 1. All right, so the path name updates right down here as I type in the individual parts. The time step, part E here, will be 1 hour. That looks good. Now I need to specify the start and end date time. So I'm going to go January 2020. It'll start at 0 to 100 hours, and the units will be in inches per hour. Well, it'll be inches, but then the type will be cumulative period, or period cumulative. Now what I need to do is paste in the data, starting here on this first cell here, representing the very first hour of the year. Well, I mean, it's labeled as the last hour of the previous year, but same thing. All right, so back to Excel. For gauge 1, I'm just going to highlight everything here, Control C, back to DSS view, click on this first record here, and then click Paste. Okay, so that pasted in all the data right here. I could expand this window, but it's hard to zoom in when it's so large. So let's click Save. No, I don't need to return to that data entry screen, but I do want to review the data. So I'm going to click right here on that path we just created, then click the graph button. Here we see the sinusoidal nature of that incremental precipitation over a 10-day simulation. So it cycles through 2 times, starting at the beginning of the year, lasting for 10 days, and then, ranging from 0 up to 0.2 inches per hour. So anyway, that's gauge 1. I need to repeat that process for the other gauges. Now, there's no reason you need to use 6 gauges. You could use 1, 2, 200, but it does cause for a little bit more work the more gauges you do. The quickest way to duplicate these is just right-click and then duplicate. And the only thing I want to change for this path is the gauge number. So I'm going to call this gauge 2, click Tab, it updates the full path, and then OK. And then OK, and then I'm good. It did mention that it made 2 copies, and I'm going to continue making copies here, just calling them gauge 3 and 4 and 5 and 6. So here's gauge 3. Okay. It's telling me that 2 records were duplicated, and I believe that's because we're starting at New Year's, and there's a single record in the 2019 year. If I go up to view and then path name parts, you see what I'm talking about here? We actually have a single record in 2019 because DSS references the end of the period. So let me see. If I open up the table, we just have a single record for 2019. And then if I open up the 2020 for gauge one, we see all the other, what would be 239 records. So let me just check here. 240. Oh, that's right, because I do have one at the very beginning of January 11th. Anyway, I prefer to have the view set to condensed catalog, so that looks a little bit more natural to me. Let me go ahead and create gauges of 4, 5, and 6. All right, so I've got gauges 1 through 6 all created here in DSS View. Now they're all using the same data because I haven't updated the data yet. So what I want to do is highlight gauge 2, and then I can go edit, tabular edit. And then what I want to do is just paste in the actual values for gauge 2 right here in this column. Back to Excel, I'm going to copy the values for gauge 2 right here, Control C. And then I'm just going to come here and Control V, should paste them in. That looks good. File, save. Okay, it's saved. And then it doesn't close, it just tells me it's saved. So I can close that. So now I have data for 1 and 2, all good and ready to go. I now need to do the same thing for gauges 3 through 6. I'm on the 6th gauge now here, and I just wanted to point something out before I finish up. If you go right click, edit, or edit up here, or click the tabulate button, if you click tabulate, it may not open up to the main edit screen. You can't make edits. That's not a problem. Just go up to edit, allow editing, and then you should be able to make edits that way. All right, let me go ahead and copy my data for this 6th and final gauge, and then we can view it to make sure that it's working. All right, Control V to paste, file, save, and then OK. Close that. Let's go ahead and plot all these and just make sure it looks like the same or similar graph we saw in Excel. All right, looks good. That's what I expected to see. Again, the values are oscillating between 0 and 0.2 inches. And then this is a 1 hour time step over 10 days. I'm going to go ahead and close DSS view. Now we can go back to HMS and assign that gauge number 1. So let's click on the folder icon here, navigate to that data directory. Okay, here's the project. Then here's the data directory. Now I have my data.dss file. Click select. And then right down here in the path name, I'm going to go click that button and then click on gauge 1 and set path name. All right, so when I click save, this should update to inches and hourly time interval. Okay, that looks good. Now we only have one gauge right now, but I can very easily go create copy, and then I'm going to name this gauge 2. Okay, so we have gauge 2 right here. The DSS file is already good. All I need to do is update the path to be gauge 2 data, which is going to be right here. I'm looking in part F, gauge 2. That's why I named part F what I did, and set path name. All right, save. Now I'm just going to repeat that process of copying and then updating the path for gauges 3 through 6. All right, that's done. I'm just going to check gauge 6, looks good. 5, 4, 3, 2, and 1. Okay. Next thing I need to do is actually add the latitude and longitude locations of these precipitation gauges. What I did is I found a northern easting location, as you're seeing on the screen here. It's some 604,000 in the X direction and then 4.72 million in the Y direction. After doing some math, then I was able to come up with the latitude, longitude for the 6 different gauges. And I'm going to type them in here. So for gauge 1, we're going with 42.7115 north latitude and then 85.6542 west longitude, and save. I'm going to continue that boring process for the other gauges 2 through 5, 2 through 6 now. So gauges 2 through 6, 2.7. So, all right. So I got all of the points located. So here's gauge 1, gauge 2, gauge 3, gauge 4, gauge 5, and gauge 6. All right. Great. The area inside that hexagon should be 50 square miles as well. All right, we have a few more things to do before we can run a simulation. So let's get started with the meteorologic model. So I'll go up to Components, Meteorologic Model Manager, New, MET1, and then I'll close that. Let's expand the MET model here in the Watershed Explorer. Right now we have specified hyetograph for the precipitation method, and we want to change that to interpolated precipitation. Again, a lot of these methods within the MET model can be interpolated. So what we're talking about here in this exercise with precipitation, it could just as easily be temperature. So there's interpolated temperature. With pressure, there's interpolated pressure right here, and so on. I believe evapotranspiration as well. Yep, there it is. If I click on this interpolated precipitation icon here, we now need to specify the method. We're going to start with inverse distance. And then down below in this table, we need to add the gauges that are going to be used for that interpolation process. So we'll just add all 6 of our gauges. 2, 3. Over on the right, there's a column for radius of influence. And to start off, I'm going to leave that blank, which basically means there's no limit on the range of these gauges with regard to being used in the calculation of precipitation at any point within our watershed. For a meteorologic model, that is all we want to do. I'm going to try to keep things simple here. I'll also change this replace missing to set to default just as a safeguard. All right, let's create the control specification. And this is going to be the same 10 days at a 1 hour time step at the beginning of the year 2020. So let me go ahead and type those numbers in here. And I'll just say the 11th at 0 hours. And then for the time interval will be 1 hour. All right. Next, what I want to do is create a simulation and then run it. I'm going to go up to the compute menu, simulation run manager, new. We'll call it run 1. That's fine. There's only one basin model, one MET model, and one control specification. All right. If I click on the compute tab, now I can make edits to that simulation run by clicking on that run 1. And the only thing I want to do here is say the spatial results are going to be yes. I'm going to record the spatial results, and that interval will be 1 hour. I think that's all I need to do. I'm going to click on the run 1. This is the simulation that I want to run, and then click compute. And it looks like it's running, so that's good. All right, it's done. What just happened there was the creation of our precipitation grid set. It may not be obvious, but we can check in the project directory. We should now have a file for that metmodel1.dss. So that's right here, met1.dss. And let's go ahead and open that up in DSS view. So you can go File Open or Control O. I'm going to go up a level to the project, and now we have met1.dss open. And we have all of our precipitation data. This is the gridded data. You could think of it as a time series of grids since it's once every hour. So I'm going to go ahead and click on all the records and then click the graph button. And what we have here is exactly what I expected to see. We have 2 points at a high precipitation of 0.17. I'm looking for 0.2. It may not quite get that high because of the influence of other surrounding gauges. But you can see we have 2 points here, 2 points here, and then our hexagon would have a point over to the side here and here. It may not be obvious at this particular hour, but as I cycle through the hours, you'll see how the precipitation in this grid works and how it changes. All right, so I'm just going to start cycling through the hours here. And as you see that the precipitation increases and decreases, and you can kind of tell where those 6 points on the hexagon lie. Again, this is probably not very natural, but it's what we're doing to kind of investigate and experiment with HMS and this interpolation process. All right, so now you need to see what's happening with the precipitation. Let's go ahead and go back to HMS and then look at the spatial results. So if you don't have spatial results turned on, you can go to View, Toolbars, Spatial Results. I like to turn off 2D. Yeah, so you can toggle that on and off. It was just the toolbar that I had right down here. Go ahead and select Incremental Precipitation and then click OK. The first time it has to build the grid cells. Okay, that looks good. Let's see. So our range is 0 to 50, and we're not going to have more than 0.2 precipitation at any 1 hour. So let me go ahead and change this first. You can go click on this gear icon, this little button right here, and then what that'll open up is a properties window. I'm going to click on this symbology tab and then change it to stretch, and then say the maximum value is 0.2 and the minimum value is 0. Click apply, and OK. All right, so now what we're seeing on the subbasin here is an image that looks more like what we saw in DSS view, where the 2 precipitation gauges at the very bottom of the hexagon represent the highest values. And it looks like I'm a little bit off the map, to be honest. I probably could have centered my hexagon a little bit further south, but it's all good. And then the lowest of precipitation right here, zero point 0.02. I'm hovering over it. And then the highest precipitation would be right here, 0.17. Okay. In fact, if I right click and check out the time series, this is what I see. It looks like it's never actually 0 and never actually zero point 0.2 because of the influence of other gauges. Keep in mind that we left that radius of influence blank, so there's really an infinite influence distance. All right, let's go ahead and play it. So here we have the precipitation. You would never see this in real life, I don't think. And that's what we did. That's what we created here. Very cool. Um, if I go ahead and zoom in, okay, so for some reason, the map display is a little wonky if I hover over a certain location, but if I just go back one frame, it rebuilds. And then, okay, we're good there. But if I zoom in, oh, okay, it's working good. So this looks good. Let's go ahead and make some changes and then rerun the simulation and see what happens. So I'm going to go back to components, go back to that interpolated precipitation. And again, we'll stick with inverse distance for now. But what I want to do is add a radius of influence. And I'm just going to say 5 miles and see what happens. Okay, I'll click save. We need to rerun the simulation. So I'm saving over the existing data, and that's fine. If I wanted to save it, I would change it to something else. And this looks interesting. We've got a bunch of colors here as before, but now we have a distinct radius of influence around each of those precipitation gauges. So you can see what's happening there. I'll go ahead and click on the play button here, and you can see the precipitation cycles throughout the 10-day simulation window. Let's do something else. What do you guys want to see now? How about 1? Let's see what that looks like. I think it's going to be kind of boring, actually. Save and then run the simulation. Okay, so now, yeah, this is not quite as cool, but let's play back the spatial results. Okay, I don't like that one. Let's go ahead and change it to a larger number, like maybe 10 miles. I changed them all to 10. Let's go ahead and run the simulation. Let's see what that looks like. Similar. I still don't like that radius of influence. I kind of think no radius of influence is the best so far. All right, we've seen enough of inverse distance. Let's check out inverse distance squared. And since we're already using a 10-mile radius of influence, which I'm sorry, it gets cut off here. I really don't need this much width to represent just a couple characters, but it's 10 miles on that radius of influence. I'll save, recompute. Okay, now let's play back that simulation. This is inverse distance squared. I like that. I don't think that's really the best. Let's try inverse distance squared with no radius of influence. So I'm going to delete all these numbers here. Okay, so those are deleted. I'll click save and then resimulate. All right. Yeah, this is inverse distance squared with no radius of influence. And what we haven't explored yet is the nearest neighbor. Let's see what that looks like. Again, no radius of influence. Okay, interesting. This is nearest neighbor. So it's a distinct value based on that region. It only takes into account the nearest precipitation gauge. And then the last one I want to try is bilinear, and I'm pretty sure I'm going to get an error when I run the simulation, but let's just double check that. Yeah, so I'm getting this error, and it basically says that the gauge network does not cover all the interpolated points, meaning our hexagon, our 6 different precipitation gauges are sort of right in this area right here. However, it doesn't have any idea what to put for locations in the watershed that are outside that hexagonal boundary. So that's just, we would need points like way outside the watershed in order to capture those areas, build the triangle, do the math, and then come up with an actual precipitation time series data set. All right, well, that was it for this exercise. What I have on the screen here is my favorite, inverse distance squared. Again, you can build grids, not just precipitation, but also temperature, pressure, evapotranspiration. There's a few others I'm probably forgetting. It doesn't have to be Michigan. It doesn't have to be a hexagonal pattern, but it is an easy way to build a grid for your meteorologic model to use in HEC HMS.